In this video, we're going to explore how partial derivatives can be estimated from contour diagrams. We've seen it from tables and from formulas, but what about graphical information? Well, imagine looking down on a surface and seeing this is the topographic map or the contour diagram or the set of level curves for a function. We're going to focus our attention initially on the point 1, 1, which is right here, and ask yourself, what is the sign of the partial derivative of h with respect to x, where h represents the surface shown here? Think about that value first, and then we'll check in a second. All right, the process for all of these partial derivative estimates is always the same. As the variable we're looking down here at the bottom increases, as that increases, what happens to, in this case here, h of x? And it's always relative to the point that we're looking at, because derivatives are local information. So imagine taking a small step from the point 1, 1 and going out in the positive or increasing x direction. Well, if that's where we're looking, we're currently at height 60. If we were to take a step on the map in the positive x direction, we would be approaching 50, which would be a decrease in h. So if we increase x, we then decrease h, and that captures the partial derivative being negative. And so our answer here is B. With that in mind, take a stab at the y direction or the y derivative, and we'll see what that is. All right, all the same logic. If we're looking at the partial derivative of h with respect to y, what we're asking is, as y increases, and again, it's always an increased step to keep the signs positive, what happens to h? Same idea. Take a step from where we are now in the vertical direction. We're at height 60 and we're heading towards the contour at height 70. If we increase y, then that leads to an increase in h, and so our partial derivative of h with respect to y is going to be positive. All right. Does it get complicated in other scenarios? Let's see what happens. Taking a look at the same surface, but now looking at the point B. So we're moving over to this location here. We will start off with the first direction, which is the x direction. Pause the video if you need to, and ask yourself what that partial derivative would be at the point B. All right. Again, we take a small step, increase in x, and if you notice the contour we're on now is at 50, and we're heading towards a height of contour 60, so that leads to an increase in h, and so that partial derivative would be positive. What about the y direction? Take a moment to think about that, and then we'll check in. All right, this one's a little bit trickier. What we have to do here is expand or zoom in a little bit. We're talking about nice clean axes, y and x here, and if we zoom in on the point B, what we would see is the contour does this. Oh my god, what the hell was that? If we focus in on the point B and the contour around there, what we would see is the contour is almost vertical. In fact, it actually is a vertical line in the xy plane. And so we have to remember the subtext of any derivative calculation, and that is for a small increase in y. Any step that we take for a derivative is going to be the smallest possible step, because what we have is the delta y approaching a zero value as part of our derivative definition. So it's not a huge step. If we're talking the derivative, it's always the smallest possible step, and that didn't affect our earlier answers, but it does have an effect here, because if we take a small step along the contour, we actually stay on the contour. Well, if we stay on the contour, that means h is constant. There is no change in the value of my function if I stay on a contour, because all the contours all the contour points are at the same height of 50 here. So if we take a super small step, we get a change in h of 0, and so the slope when we take that step is 0 as well. So there's this fine line between the direction of positive slope. In fact, any direction that we went to the right here would be positive slopes, and then there's this one special direction seen on this diagram here is parallel to the contour or taking a step along the direction of the contour where we're going to have 0 slope. If you think about this on a map, if we built a road that followed the contour, if we follow the road, by definition it's going to be a perfectly horizontal or flat road in the going up and down sense. And so if we follow that road for just a tiny step, we're not going to see any slope, and so the partial derivative is going to be 0. That can take a little bit of practice. Definitely take a look at the practice problems, which will have some questions related to this as a way to test out your understanding. All right, now we can also go the other direction and ask where a particular derivative seems to be particularly large. Well, a large derivative is what we would interpret as a steep slope. We would also infer, because we're talking about derivatives, that it's a steep positive slope. And for us here, that means an increase in x implies a large change, or large increase specifically if we're looking for positive slopes, a large change or increase in h. Well, those kinds of changes occur where? Well, on a contour diagram we know that that occurs when we have tightly packed contours. But not just any contours or packed in any way, tightly packed so that when we take a step from left to right, we cross more contours. And if we take a look around here, it certainly seems like a point here, if we take a step to the right, we're going to be passing contours fairly quickly, and pretty much any point in this region is going to have steep uphill slopes in the x direction, in the positive x direction, and that would imply or capture exactly what we mean by large partial derivative of h with respect to x values. Notice we probably would not include this region over here. This region over here, if we take steps in the positive x direction, it's still steep, but this would be steep downhill x slopes. And this would imply large but negative, which we wouldn't usually just call large negative partial derivative of h with respect to x values. So that would be something that we can identify now on a graph, especially a contour diagram. And it's the kind of thing, again, if you think of this as a topographic map and walking around the surface, if we are walking on the map, we should be able to visualize what the surface or the hills and valleys that we're walking through look like. If we're here, we would be walking up the hill, and it would be a steep uphill. And here, if we walk in the positive x direction on the map, we'd be walking in a steep downhill direction. In any question on a test or practice problem, we'll try to be precise about the sign that we're looking for, but that captures nicely what the partial derivatives mean and connect it back to the contour diagram in this example here.